I remember lying in my backyard as a kid, just staring up at the night sky. And I honestly thought the universe was this high contrast photo, just bright white dots on a pitch black background. But looking at the research for today, it turns out I was completely missing the picture. The solar system isn't black and white at all. It's absolutely drenched in color. We just need the right eyes to see it.
That is the perfect way to start this deep dive.
Yeah.
Because we aren't talking about pretty pictures. Not really. We're talking about chemical maps. We're analyzing how astronomers use, well, invisible light,
Mm.
specifically visible and near infrared, to figure out what the solar system is made of, all without ever touching the rocks.
It's geology from millions of miles away, and the main tool here is something called reflectance spectroscopy.
Right. And the key thing to remember is that asteroids, they don't have light bulbs. They don't emit their own light. They just reflect sunlight.
Mhm.
But they're picky about it. Different minerals on the surface absorb very specific wavelengths of that light.
So when we look at the light that's bouncing back, we're actually seeing what's missing, the gaps.
Exactly. Those gaps are the spectral fingerprint. For instance, common rocky silicates like olivine and pyroxene, they absorb light right at 1 micron and 2 microns. You see those dips in the data, you know you're looking at rock.
And the research shows that if you look a bit further out, say between 2.7 and 3.1 microns, you find these water bands.
That's the signature of hydrated minerals.
Hmm.
Actual water, well, water molecules trapped inside the rock structure.
It really is like scanning a barcode at the grocery store, except the checkout counter is Earth and the cereal box is floating out in the asteroid belt.
Okay. But here's where it gets more nuanced. Those barcodes, they aren't static. There was this fantastic paper back in 2005 that highlighted a phenomenon called space weathering. See, asteroids don't have an atmosphere for protection, so they just get hammered by micrometeorites and solar wind.
Which changes the paint job over time.
It does. It generally makes the surface darker and, crucially, redder. The research actually put a number on this. They found a surface that's a billion years old reflects about 15% more light at that 1 micron wavelength compared to a fresh surface, one that's maybe only 5 million years old.
The red shift, but the aging kind, not the cosmological kind. And this actually solved a huge mystery that had bugged astronomers for decades, right? The S-type paradox.
It did. A massive one. We knew that S-type asteroids out in space and the ordinary chondrite meteorites we find on Earth were made of the same stuff. But the asteroids looked red, and the meteorites looked, well, more neutral or even bluish.
Because the meteorite is the fresh insides that broke open, while the asteroid is the sunburned, weathered exterior.
Precisely. Understanding that color shift finally allowed us to connect the dots. The rocks in our museums and their parent bodies in space.
Speaking of connecting dots, if you're trying to link complex systems in your own business, whether that's AI training, automation, or software integration, you should check out our sponsor, Embersilk.
Embersilk is fantastic at uncovering where AI agents can actually make a real impact on your workflow or your personal life instead of just adding noise.
You can find them at embersilk.com for all your AI needs. So we can tell what these rocks are made of, and we can tell how old they are. But recent data suggests the neighborhood is a lot messier than we thought.
It really is. Astronomers use what's called the Demeo taxonomy to sort these rocks. It's like a cosmic filing system, S-class, C-class, X, D, and so on. But a very recent study, one from just this year, sort of shook up the filing cabinet.
They surveyed 80 near-Earth asteroids, right?
They did, and the breakdown was surprising. They found 46.3% were S-complex, the rocky inner-built types you'd expect to find near us, but 26.3% were C-complex.
Wait, C-complex? Aren't those the primitive carbon-rich types you usually find way out in the cold outer belt?
Exactly. Finding that much primitive material right here in our backyard is pretty much definitive proof of planetary migration. The solar system isn't a static tray, it's a mixing pot. The gravity of giant planets must have dragged these outer rocks all the way in.
Now, I know some people might be thinking, this is all just interpreting squiggles on a graph. But we have ground truth on this now. We've actually gone there.
And that validation is crucial. We have missions like Dawn at Vesta and OSIRIS-REx at Bennu. A key study a few years back actually validated this by testing 17 specific spectral indices on lab data first.
And it matched up with the real world.
Perfectly. Even on Bennu, which is just a messy, complex rubble pile, the fingerprints for hydration and organics held up. It proved these spectral maps are accurate. We really can trust the rainbow.
I love that. Trust the rainbow. So I want to leave you with a final thought. We know red means old and weathered. So if we look through a telescope and spot a bright blue asteroid, what are we actually seeing?
You're likely looking at a fresh bruise. a recent violent collision that stripped away that old weathered skin and exposed the fresh blue rock underneath.
The universe is constantly writing its history in light, and we're just now, finally, learning how to read it. It's an incredible time to be curious.
It certainly is.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.